All right, so when you guys did this, you had to find the true speed and direction if the pilot is heading here. So your theta value had to be 135 because you're starting at 0 and then this is your direction, right? If it's 45 degrees here, theta is going to be 90 plus 45. So this is your velocity of the jet. To find the true speed, you have to have the true velocity vector. So your wind is the same. So then when you add them together, this is your true velocity. Now to find the true speed, what do? Yep, you take the magnitude of the true velocity. Okay, so your true speed, 781.05 miles per hour. Thumbs up if you guys got that. Okay, all right. Now, the tangent was a little bit trickier, so I am going to talk you through that a little bit more. So when you're finding the tangent, you set up b over a with the true velocity vector, and then you got negative 48.9 degrees, okay, which would be here on the diagram. But the jet isn't going this direction, right? The jet isn't going southeast. It's going northwest. You guys with me on that? Okay, so this negative 48.9, it's in the opposite quadrant. So what do we add to it? We're going to add 180 degrees. Yeah. So it needs to be in quadrant 2. So for it to be in quadrant 2, we add 180 degrees. We get 131.1 degrees north of east. Okay, so if you just got here, I'm great with that. Okay, I'm going to help you get the final answer. So we're going to add 180 so that we're going north of east. The only problem with this is, if you tell a pilot you're going north of east, but you're really going northwest, that's confusing. So with your bearings, each quadrant is 90 degrees. So anything larger than 90, you do have to subtract in order to get the correct bearings. So if you take 131.1 and you subtract 90, you're going to get the jet going in this direction, which you can call 41.1 degrees west of north. You can do north 41.1 degrees west. Or did any of you use like the vertical angles here? Okay, so if you know that this is negative 48.9, using your vertical angles, we know that this is 48.9 degrees here. Okay, and for that one, you could say you're going west, 48.9 degrees north. Okay, so that would be another way you can do it. As if you know this is 48.9, vertical angles are congruent. Back to our geometry days. Okay, and you could recognize that from your drawing, which is why the diagram is important. Okay, and then you could also say 48.9 degrees west of north. All right, any additional questions for me on that one before we do part F together? All right. And then I will be making a video of this, so if there's anything you need to look back at again, or if you want to copy some more down, you will have that, okay? All right, so this one says, in what direction should the pilot in example 3 head the plane for the true course to be due north? Okay, so we have not done a problem like this before, where it says in what direction. So if it says in what direction, what we have to do is find the theta. I'm going to come in tomorrow with a walker. Help me get around better. All right, so in what direction should the pilot head the plane for the true course to be due north? When it says true course, that means you want the true velocity vector to be north, okay? So we're going to take our straight edge. And we're going to just model this picture here. Okay, so this is going to be the velocity vector, the true velocity, which is the jet plus the wind. If they're asking you in what direction, you are going to find theta for the airplane. Okay, so you're going to find the theta in the airplane vector. Okay, so the wind is going to stay the same. Okay, so your wind is 27.5, 47.63. Okay, so that's the same that it's been throughout this example. Okay, the jet that we're trying to find, we know the magnitude. The magnitude is 765, but we're going to do the cosine of theta, 765 sine of theta. Okay. So our vector, our velocity vector is going to be the jet plus the wind. So when we add those together, we have 27.5 plus 765 cosine of theta. So it is an expression. And then see if you can write down the vertical component. Okay, so we're going to have to find a way in order to solve for theta, and it's going to be based on where you want to go. So based on what we know about the wind from last time, remember that the wind was flying in the direction north 30 degrees east. Okay, so the theta value was 60. Okay, we're going to draw that on our picture. Okay, this is the wind. Okay, and then we'll put the jet on there in a moment. So if you want the course to be due north, okay, that means you want to be going straight this way. What type of winds would push you off course? This pen is our plane. Winds coming from which direction? Right or left, right? East or west? Because if it came from the south, it would just make the plane go faster, right? If it came from the north, it would just make the plane go slower, but you'd still be going in that direction. But if you had a wind that was going towards the west, then the plane would start to go this way. If you had a wind coming from the west to the east, it would be going this way. So what you want to happen here is you want the horizontal component to be equal to 0 in order to head due north. So this is the horizontal component. So we're going to write that down. So you want the horizontal component to equal 0 in order to head due north. Okay, so the horizontal component, horizontal is east and west, okay, left and right, east and west. So those have to be 0. If not, it would knock it off course. Okay, what that means is there'd be no horizontal forces. Acting on the plane. So it's always the opposite of where you want to go, okay? So if you're going in a vertical direction, north or south, it's the east or west that has to be 0. Okay, so we are going to set that equal to 0, and we are going to solve. Okay, so we're going to take this value here. I'm going to do that over here. So we're going to set the horizontal component equal to 0. 27.5 plus 765 cosine of theta equals 0. Okay, so go ahead and solve that for theta. You have all the skills to be able to solve that for theta. You are going to need your graphing calculator or a calculator for graphing. All right, so let's do our calculation. Okay, and then we got 92.06 degrees. All right, so we're going to have to determine the bearings. So you might remember from last week we talked about this dashed line is the diagonal of the what? The parallelogram. Okay, so what you have to do is you have to imagine that that's your diagonal. And sometimes I just take my pencil and I draw it. So this would be like part of the parallelogram here. The other part of the other side of the parallelogram, that is your jet. Okay, the other side, because if they start at the same place, now you can see, okay, where that should be. Now, remember how the jet was 765? So really, this compared to the wind, like this would be a lot different, but you can still see what direction it's going in. Okay, ours just is not very accurate, but it is going to be going in this northwest direction. Okay, so sometimes I just like to draw a picture so you can see what's happening. If you get 92.06, you are finding that this is your jet here. This entire angle is 92.06. Okay, it's your north of east, right? Is what it finds. You start at 0, you go to the 92.06. But if it's greater than 90, you have to subtract 90 because you are crossing over into another quadrant. So if you subtract 90, you'll get 2.06 degrees. And now you can see the direction that it's going in. So you can say 2.06 degrees west of north. Okay, or you could say north 2.60 degrees west. Either one of those would be fine. Okay, any questions for me on this part? Okay, and then we're going to head over to the next page. All right, so we're doing resultant forces, and then we're going to save tension for tomorrow. Okay, and we're going to draw a picture to accompany our work for each of these. Okay, so in example 1, a man is pushing a lawnmower with a force of 30 pounds exerted at an angle of 30 degrees to the ground. So when you're pushing the lawnmower, the force is going towards your ground here. Okay, and said it's making a 30-degree angle. If you want to draw a guy pushing something, you can. My guy always has a very long torso, but he's happily mowing the lawn here. And then we have to find the horizontal and the vertical components. Okay, so the horizontal component is the magnitude times the cosine. Oops. I'm just going to start that over. So the magnitude times the cosine and the magnitude times the sine. Okay, so the horizontal component, 30 cosine of 30 degrees. Vertical is 30 sine of 30 degrees. Okay, if you had to do this in a no calculator section, you could do that just based on your knowledge of the unit circle. We know that 30 degrees is going to be root 3 over 2, and the sine at 30 is 1/2. Okay, so if you have 30 over 2, this would be 15 root 3, 15. Okay, or you could write it as a decimal as 25.98, 15. Okay, and then this is your horizontal component. This is your vertical component. Okay, so either form would be fine for this. All right, and then for example 2, I want you guys to do this first part where it says a river flows south at 3 miles an hour. The swimmer attempting to cross the river heads due east, swimming at 2 miles an hour relative to the water. Find the true velocity of the swimmer as a vector. So true velocity is going to be the swimmer plus the river. Okay, so I'm going to let you find the vector for the river and for the swimmer, and then we will find the true one, okay? All right, let's check in and make sure you guys got the right angles. So for the river, which is right here, okay, think of this on your grid, right? If this is going straight down, okay, that's going to be either negative 90 degrees or 270. Okay, and then here's your swimmer, which is right at 0 degrees. Okay, so then for your river, you get 0, negative 3. For the swimmer, you get 2, 0. And then when you add them, the true velocity is going to be 2, negative 3. Okay, how'd that go? How'd the angles go? So this is the true velocity of the swimmer. It's the swimmer in relative water and then the river. Okay, so how is true velocity different from true speed? Well, remember, true velocity is the resultant vector. Okay, so it's the sum of the object and the force. True speed is the magnitude of the resultant vector. Okay, so sometimes they'll ask you for true velocity, sometimes they'll ask you for true speed. Okay, suppose that in example 2, the current is flowing at 1.2 miles an hour due south. In what direction should the swimmer head in order to arrive at a point due east of his starting point? Okay, anytime they're asking you what direction, that means you're going to find the theta. Okay, and in this case, it's going to be of the swimmer. All right, so we're going to draw a picture for that as well. Okay, so the river is going to be the same. You want to head somewhere due east. Okay, so if you want to head somewhere due east, I better use my straight edge and be safe. Okay, if this is where you want to go, I'm making it the dashed line because that is your resultant vector. Okay, and then we know that the swimmer, or not the swimmer, the river is heading south. And this, in this case, it said it's 1.2 miles an hour. So this is going to be your river. Okay, and we don't need the other part of the picture until we go to calculate. You can do the other parts without it, or if you want to do it at this point when you're doing it on your own, you can. Okay, so the swimmer, we don't know what the theta is. So all we have is the magnitude, which is the speed, 2 cosine of theta, 2 sine of theta. The river we do know because we know that the speed is 1.2, and then based on the position, if it's going south, what did we say that angle is? We just did it. Yeah, you can do negative 90 or you can do 270, whichever one you want. Okay, at 270 or negative 90, the cosine is 0 and the sine is, so the cosine is 0, the sine is negative 1 at 270, right? Okay, so the river is going to be 0, negative 1 times 1.2. Okay, and then you are going to find the resultant vector. So when you add them together, 2 cosine of theta plus 0 is just 2 cosine of theta. So you're finding the resultant, horizontal plus the horizontal. Here you're going to do the vertical plus the vertical. Okay, so vertical is 2 sine of theta plus negative 1.2, so we can just put minus 1.2. Okay, now it says that you want to go due east. Okay, if you're going east, what component is 0? Yep. Okay, so if heading due east, okay, if you want to go this way, the only forces, I guess I should do this, if you want to go this way, the only forces that can knock you off is if it points you to the north or if it points you to the south. Okay, so if you're heading due east, your vertical component has to equal 0. Okay, it's always the opposite forces that you want to be 0. That's what will knock you off course. Okay, so this is your vertical component. So we're going to set that equal to 0. And we're going to solve. So when you solve, you add the 1.2 and you divide by 2. So is it okay if I just do this to start? Add the 1.2, divide by 2. And then we are going to use the sign inverse. Okay, and then Farah, will you tell me what you got to that for that rounded to the nearest hundredth? Good. Okay, now to find the direction, you can use what we just talked about, how this is going to be a parallelogram. So you just are creating the equivalent side here, and this is the direction it should be heading. Which makes sense, because if the river is going south, right, if you start heading this way, and then the river is pushing you down, then you get to go east. Sorry, I guess you couldn't really see the end of that, but all right. So the bearings for this is going to be north of east. So 36.87 degrees. You can say north of east. You can say east 36.87 degrees north. That would be equivalent. All right, and then the last thing we're going to do today is talk about some forces. So the force is a push-pull on an object. The resultant force is the vector sum of those forces acting on an object. And equilibrium is a state in which opposing forces are balanced. Okay, so there are going to be forces that are called F1, F2, all the way up to F sub n, just depending on what your problem is. They are acting at the same point P, and they are in equilibrium if the resultant force is 0. Okay, and what that means is if you add these together, F1 plus F2, all the way up to F sub n, okay, then you will be in equilibrium. So we're going to be finding some of these forces. So in part A, you have to find the resultant forces acting at P, and in B, the additional force required, if any, for them to be in equilibrium. Okay, so if they're in equilibrium, the sum would equal 0, okay, when you add them together. All right, now in the first one here, we're going to plot these vectors. So our point P can just be in the center here. Let's go ahead and scale by halves. Okay, so if you have 1, -1, if you start here at point P, and really it could be anywhere, but it's just going to be easiest for you to start at 0, 0. So if you have 1, -1, you go over 1, down there, down -1, and you can draw your vector. This is f sub 1. And then the second one is over 1, up 1. This is called f sub 2. Okay, and then the third one, -2, 1. Okay, so left and then up is your f sub 3. Okay, we plotted the vectors. In part A, we're going to find the resultant forces acting at P, which just means we're going to find the sum of f sub 1, f sub 2, and f sub 3. Okay, so we're going to add all the horizontal components. 1, 1, -2, and then -1, 1, and 1. Okay, so here we get 0, here we get 1. Okay, this is the resultant forces. Okay, for part B, we're finding the additional force required to be in equilibrium. So you're answering the question, what would you add to this to get 0, 0? Okay, so in this case, it would be 0, -1. And then we call this F sub 4 because you already have 3 forces. So this would be the additional force. So your opposing forces are opposites. Okay, so if you added these together, you would get 0, 0, and you would be in equilibrium. All right, and then for 2, you are going to have to find what F1 is using the magnitude times the cosine. Same thing for F2. You're going to have to do the magnitude times the cosine, the magnitude times the sine. Okay, so I'm going to give you a moment to do that. Okay, so let's just double check that you did that. So it's the cosine of 45 and then 5 sine of 45 degrees. Okay, 5 is labeled right there as the magnitude. Now don't be surprised when you get the same thing for each one because the cosine and the sine at 45 are the same. Okay, so you should have 3.54 and 3.54. Okay, now when you go to F2, don't use 15. What do you have to use as your theta? 195. Okay, so theta starts here and ends there. So in this case, your theta, you have to add 180 to the 15. Okay, so now you have, this is a magnitude of 3. So 3 cosine of 195 and 3 sine of 195. Okay, so theta always starts at the 0 degree mark. Okay, so when we calculate that, you're going to see too the direction of the vector. If you have a negative, it's in quadrant 3, so it should be negative, negative. Okay, if it's in quadrant 1, it should be positive, positive. Okay. All right, so then for part A, when you're finding the vector sum of F1 plus F2, you're just going to add the horizontal components together to get 0.64. Okay, so you add the horizontal and the horizontal, you add the vertical and the vertical, and you should get 2.76. Okay, any questions for me on part A? Finding the vector sum, the sum of the forces. Okay, then for part B, it's your opposing force. So it's always going to be the opposite. Okay, we'll call this F sub 3 because we had 1 and 2. So this will be the third one. So this will be negative 0.64 and negative 2.76. That's what makes it equilibrium. Okay?